welcome to the series on computer science. As a part of this series, today we will be seeing on artificial intelligence, and this is a course on it. And as a part of this course, in this module we will see the greedy best first search, which is a part of informed search. In the last module, we saw uninformed search techniques, and this was the question asked. Like, consider a state space where the start state is number 1 and each state k has two successors, namely 2k and 2k plus 1, and from that the first question was draw the portion of the state space from states 1 to 15. Second, suppose the goal state we assume is 11. List the order in which the nodes will be visited for various search techniques. One will be BFS, second will be DFS, third will be iterative deepening. And lastly, there was also a question on the bidirectional search, how will that work and what is the branching factor from each of the directions. So, let us start with the binary search tree. It would be something like 1, and at this section this is 2k, on the left side is 2k and on the right side is 2k plus 1, which is 3, and 2 into 2 plus 1, this would be the right side, 2 into k, 2 into 2 4, this is 2k, and this side would be 2 plus 1, it is 5, this would be 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So, the question is, this is the start space from 1 to 15. This is the start stage, which is 1, and the goal state is 11. So, given this tree, can we identify what will be the BFS? BFS would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, that is going to be the BFS, and a DFS would be 1, 2, 4, 8 and then backtrack 4 and then 9, backtrack 2, 5, 10, backtrack, and here 11. This is going to be DFS. Iterative deepening or depth limited will be first, if we say suppose if you take the depth limited search with limit as 3, then this is going to be the limit 1. In limit 1 it will search depth wise, and limit 2 it will go depth wise and within that breadth, and limit 3, in this limit 3 it would find through the depth first search as 11. In iterative deepening, it would be very similar to that of DLS, but at each stage there will be the iteratively it would start. So, at the first stage, first when the limit is 1, it would go into BFS, in the second in the next iteration at this stage, and the third iteration at this stage, that is via the iterative deepening search. For the bidirectional search, it would be the branching factor for these direction is 2, and in the forward direction it is going to be 2 because it is via this route and this route, whereas through backward it is going to be 1 because from 11 it is going to go this way. So, that is typically the answer to the last week's module. Okay. Coming to this week's module, this is the greedy best first search, which is a form of informed search technique. But before we get into the greedy best first, let us remind us of the evaluation function that we saw, where f of n is equal to g of n plus h of n, where f of n is the evaluation function and g of n is the actual value and h of n is the heuristic value. Now, for the greedy best first, we have to take only the h of n value, and we will assume g of n value as 0. Therefore, evaluation function is going to be only with respect to the h of n value. And for greedy best first search, we have to in this case we are going to remind us of the priority queue with the minimum cost. So, we are going to use priority queue with minimum cost. Let us take this example. Suppose this is the starting stage. This is a simple tree, like a graph structure where S is the start and G is the goal, and the numbers marked here above each of these nodes, these are going to be the heuristic value. Now, from S, if we see, there are 3 branches that are branching out, 1 to A, C and D, and with each of the heuristic value as 6, 6 and 3. That the meaning is, from S, suppose I am at S, the cost expected to reach at A is 6. This is the estimated cost, this is the heuristic cost, it is not the actual one. So, greedy best first will always act only on the heuristic value. So, what it typically does is, at starting point it will take the least possible heuristic value and branch out. So, this is the problem that we are going to see it today, and we will go step by step. It's like we will assume how a machine would see this graph. Initially, we have to create this graph to a machine. Suppose we want to write a code, we want to write the program for this graph. So, the first one would be, the step 1 is initialization, where all the nodes here are created. So, we have 2 blocks here, one is the node, another one is the neighbors. The node we are declaring as S is equal to node S7, which means node is name is S with the heuristic value 7. So, we are giving this block of the code to create the nodes. Now, from each of the nodes there are neighbors. For S there are 3 neighbors A, C and D. So, those 3 neighbors are added here, S dot add neighbor A, C and D. Similarly, for A the neighbor is B. So, for A the neighbor is B, and for D the neighbor is B, D the neighbor is B, and for B the neighbor is G, for B the neighbor is G. So, the first step, we are adding all the nodes and adding all the neighbors. So, via code, this is a right hand side is the actual code in Python that we are representing, where the name of the class is node, and we are giving the name of that node. The name here meaning S is a name, A is a name, B, C, the name of the node is the cell dot name, and the heuristic value, that is 7, 6, 2 are the values that is attached to the name, and the neighbors that we saw in the previous slide, that is given as a list. Now, we have 2 functions. One would be the, we are assigning the cost. In this case, if we see the cost, we initially we are assigning as 1, and we are appending that cost to the neighbor, that where the cost is this is the initial cost, and whenever we add this cost, this function is called, the cost is again initialized only to 1, because we are not going to add the cost anywhere, we are not going to add the heuristics cost. So, it is always initialized to 1 and reset to 1. Now, and the next step, we are going to declare some variables. I earlier said that we are going to maintain a priority queue. So, for that we will be using heap queue dot heap push, but before that we have the 2 major variables. One is called the open list, another one is called the closed list. Open list is where we are going to put the nodes that are going to be visited. Say initially S has to be visited because it is at the start. So, initially this S will come into open list. Now, after visiting, that particular node will get into this closed list. Now, the third line, this is where the priority queue is working with. Now, in the from the open list, if you see the open list, this open list will be the prioritized one after the update, and the structure is start dot heuristic start. This is the value that we see 7, 6, 2, those value, and initially we are going to put the start. So, the start is the initial portion that is given, but later on, as in the code, if we see, it would be the name of that node, and this variable came from, it is a dictionary to store the visited node and the parent, or the expanded node along with the parent. In this case, the start, for the start, nothing is there as a parent. So, start dot name we are initializing with none. So, this is regarding the variable section. Next, this is the overall algorithm, and this is what we are going to explain step by step in the forthcoming slides. Now, if we look, I will just give an overview of the entire code, and then if time permits, we will again come back to this slide and take a look at it. Now, if we see the first line, while the open list is available, okay, here the first two variables, this is the underscore with the current node is heap queue dot heap pop. This represents the priority queue with the minimum cost. What it does is, it takes the open list from the open list with the heuristic value, takes the minimum and puts the value of the value in dash and the name of that node as the current node. Now, in the next step, it checks whether it is a goal, the expanded node is a goal. If it is a goal, it does certain operations where it is going to be from this variable called came from, and within this came from, this has all the parent information. So, this parent information, through this parent information, it gets the path. Once the goal is found, the parent's path, through the parent's information, the entire path is going to be constructed from this dictionary, and we are going to reverse that, so that it is from this first to the last. Now, if it is not goal, it comes here. If not goal, then the expanded node will add to the closed list. Now, after the closed list, it will check for the immediate neighbors. If the neighbors, and if the neighbors is not in closed list, again push that in the open list, and this again will check for the minimum cost. This is again the priority queue, and if the neighbor is not in the parents tree, add that to the dictionary, which is the variable came from. So, this goes on and on until the goal is to be found. So, we will go through this algorithm in detail with that example in the forthcoming slides. So, let us take this example. We saw in step 1 earlier, where we initialized that with the entire nodes and the neighbors. Now, in the second step, the open list is initialized. So, first it is going to be an empty list, and closed list also is going to be an empty list. This came from is a dictionary which is initialized to track the path. So, these three things. Now, at the start, push this S node, start node, here we are going to say S node to this open list. So, once we push the S node, this is the priority queue. This adds S with a heuristic value of 7 to the list. So, our open list now will have the list of 7 comma S. So, this will have 7 comma S. Now, open list is 7 comma S and closed list is initialized to 0, and came from, it is before S, it is none. So, therefore, this is the nothing is there for the parent S, that is also done. So, in the step 3 is the first iteration, where we start with the loop pop S. So, we saw S at the root. Now, if we pop S, node S is pop, because in open list there is only one node which is S that is being popped, and it is one node and it is the lowest. and S is not the goal, the second part of the code if you could remember, and its neighbors are A, C and D. So, this would the branching out as A, C, D. So, S is not the goal. So, the neighbors are A, C and D are expanded and added to the open list. So, if you see, the open list will become like this 3D. So, this will get a value of 3, D's value is 3 and A value is 6 and C value is again 6. So, after this step we will have these values open list and closed list. We have visited S. So, the value the name of the node from open has come to the closed list with S and came from, it is the dictionary where we are maintaining the parents. Initially we are having S with none. Now, that is being appended to D with S because D's parent is S, C's parent is S and A's parent is S. So, we are having D with S, A with S and C with S. So, D's S and C's parent is S and A's parent is S. We are appending it in the came from dictionary. In the next iteration, if we check the previous iteration, the lowest one, this is the priority queue, the heap queue, the lowest one is 3. So, actually this is going to get branched out, this has to be popped out. So, node D is popped out from the open list because it has the lowest heuristic value. Now, D is not the goal. So, its neighbor B is expanded and that is added to the list. Now, the open list will have 2B. Remember, we already have 6A and 6C, this is there in the previous slide. Remember, this is the previous slide where we had 6A and 6C, D is getting popped out. Now, that same 6A and 6D is already there and along with that the node B with heuristic 2 is pushed. Now, after a priority queue with minimum cost, this comes at the first, 2 comma B will be the first, this is after updating the open list, this is the one where 2B is the first one. Now, the closed list, suppose we have popped D, we have visited, that D will come at this stage. Now, the came from now will have S none, D S, the same thing where we had until C S D D S, and extra that we have from this iteration is D. For D, the child is B. So, B parent is D, that we are specifying here. So, this is the second iteration. In the third iteration, because B is the minimal value, remember this is the priority queue, we already have 6A and 6C, now B is the priority queue with minimum cost, B is going to take place. And suppose I draw the diagram, initially we have the tree structure as S, A, C and D, S A with the cost of 6, C with the cost of 6 and D with the cost of 3 is the second iteration. After this we had B with 2 as the heuristic value. Now, this is at this stage, after popping out D, this is the stage. Now, B has to be expanded and naturally when we expand, B is not the goal. So, G has to be given. Now, this is the fun where the heuristic cost of goal is 0. So, 0 comma G will come into the open list and this is at the starting stage. So, this has to be popped out of the priority queue and the closed list will be the 3 things S, D and B, and came from will have another append from the previous one and this one, where for goal B is going to be the parent and this is being returned here, where G is the child of B. Now, at this stage we have to pop out the goal with the 0 cost. Now, when G is popped out from the open list, it is actually the goal, and since it is the goal, if we remember the top portion of the code where we have to reconstruct the path, and the path will be, if you check the path, G is B and B is D, and then D is S and S none. Okay, it would go through A S. Okay, this is the entire path of it, but from this dictionary the path will be reconstructed as G, B, then D, then S. This is, and this will be reversed, and remember the reversed one we gave it as -1 in the code. So, when it is -1, the result would be S, D, B and G, which will be S. If we reverse this, the actual path will be from S, D, B and G. So, the final path is printed at last. So, this is how the algorithm of greedy best first is working. Again, if we will go back to the code and just revisit this such that we are able to understand it. So, again the first part is where the priority queue is set up, and this part is where the path is going to be found. So, at each stage we are appending the parents, and at the last we are reversing it, and if the goal is not found we are adding it to the closed list, and for each of the expanded node we are finding the neighbors along with the heuristic value, and we are finding using the priority queue the minimum heuristic value, and this loop continues, the whole loop continues until the goal is going to be found. This is the example of greedy best first search. Now, we will see the book example of map of Romania, where on the left side of this, okay, this part of us, this is the map where we are seeing with the actual cost that is given, and this is the actual G of n value, and the straight line distance on the right, it is going to be the heuristic value h of n. So, for greedy best first we are only going to see this value, which is the h of n value, where we are going to start the question goes like this: can we find using greedy best first where the starting state is Arad and the end state that ends with Bucharest. This is the end state or the goal. So, can we find the path from this point, the start to the goal, which is Bucharest, through greedy best first search, and for that we are going to use only the heuristic value h of n. So, let us see how it goes. We will start with Arad, and if you see the value of Arad is 366. So, at the initial stage it is 366, and the branches that it gives out are the 3 cities starting with S, starting with T and starting with Z, which from Arad, if you see the 3 branches starting with Z, starting with T and starting with S, these 3 cities along with these values is 253, 329 and 374. Now, the minimum cost again with the priority queue is going to be 253, which is the city. So, again if we expand that, we get the same A, same Figueres, another city O and RV along with the heuristic. Remember, all these are going to be the heuristic cost, and when we branch out these heuristic cost, the minimum value is 176. So, we have to branch out the city of Figueres. and when we branch out Figueres, we get this as the goal, and this is the starting point and this is the goal. Now, if we see the actual cost, it is going to be 140 plus 99 plus 211, which is going to be 450. But if we see this in the graph, so the path that we went is Arad, Cebu and Figueres. But if you just look at the map, this is not going to be the optimal one. In fact, another path which is right here, this will be the optimal path, but greedy best first search, it will give the solution, but it may not be optimal because it works only with the heuristic value. Now, coming to the performance measure, the first performance measure would be completeness. Is it complete? This is actually the completeness. The reason is it is not complete. No. Why? Because it can get stuck in the loops. Take for example, this graph where 1 to 2, 2 to 3 and 3 to 1, it can get stuck in the loops and cannot come out. So, it is not complete. A time complexity, it is order of b power d, although a good heuristic can be an improvement. The space is b multiplied by d. The reason is we can store only that part of the path into the memory. So, we did not store the entire nodes in the memory for the entire traversal. Optimal? No, it is not optimal. As I said earlier, the distance from Arad to Bucharest through the other path is the shortest. Now, so that is the summary of this session, where in this session we had the greedy best first search, where in greedy best first search the f of n will function only based on the heuristic value h of n. In the next session, we will be seeing A star search, which will have both g of n as well as h of n. Okay, I will see you in the next session with the explanation of A star.